Everyone, and welcome to lesson 13.1. Today we are going to talk all about our rational functions and some features of their transformations. So if we look on page 167 in our books, we see this problem about a cistern or a large cylindrical tank, and we see that this cistern, they're looking to find the amount, the height of it, the function h of x, if it's holding 25 meters cubed of water. So when we write this function for this cistern, h of x is going to be our function this time. We would take 25 and divide it by pi r squared to help us find that ratio for the height. And what ends up happening then on this graph, if we actually look at it, we see that this is what we would call a rational function. And we have that basically two different polynomials, 25, x to the 0 power, and then r is, or in this case, x squared is our polynomial then kind of in the bottom of that. And again, we see that rational nature of this based on a couple of things. First of all, if we look at our end behavior, as x's are going to either positive or negative infinity, both the right-hand side of the graph and the left-hand side of the graph, we're noticing that our y values are going towards 0, right? They're not touching 0, but they're getting really, really close to that horizontal asymptote area. We also notice that there is a vertical asymptote at x equals 0. So in the middle here, we are approaching 0, but we are never actually touching it at that vertical asymptote. There is a horizontal asymptote this time at y equals 0, again, which is kind of affecting that end behavior. And then there's also end behavior around our vertical asymptote, because we could say as the x's approach 0 from the left, right? So this to this means from the left. We notice that our y values are going up to positive infinity. As we approach 0 from the right-hand side, so again, if you see this little plus, that means from the right side of it, again, we're going up towards positive infinity. So there's not only end behavior at the end of our graph as the x's are getting bigger or smaller, but we also, with these rational functions, have end behavior around these asymptotes. And now normally the domain and range on these, the domain would be everything except x is not going to equal 0. But for the sake of this problem, because it's a real life problem, we would say that we would just want the x values to be greater than 0, because officially we're not going to involve negatives in a real life problem like this. And then our range, whether it's related to this problem or not, again, is going to be all of your y values greater than 0, not or equals to, because we're never actually touching that horizontal asymptote. But that'll work for the real life problem as well. Now, if we start looking at some other features beyond just this real world rational example, okay, what's happening with some of these other types of functions, okay? If we look at this next one, notice this time there appear to be two different horizontal asymptotes. So this one, we've changed it up a little bit because we added in a slightly different denominator on this. And what we're going to notice this time is, because if we factored this, we'd have x times x plus 2. What this is going to do is this is going to make us have two different vertical asymptotes, one at 0 and one at -2 this time. And what we notice on this one is that is going to change the amount of our asymptote end behaviors we talk about, because we would have to talk about our x's as it approaches -2 from the left and -2 from the right-hand side. Now, both pieces as we approach there happen to go to positive infinity, but we would have to talk about both sides. Same way we would talk about 0 then from both the left and the right as well. And in both of these cases, again, the y's are going up to positive infinity, but you would have to talk about both ends. Our overall end behavior is going to be based on the horizontal asymptote again. So this time, because we have a horizontal asymptote at y equals 0, we notice that our end behavior of these graphs as x's are getting bigger and smaller, again, is approaching that value at 0. Okay, so a couple extra things to note with that change of our asymptotes and how it affects things. Now, in general, we have some things that we can predict based on our function. So if we look for this first one at our parent function here, 1 over x, the parent of the rational functions, what we notice is that our denominators here are, again, shifting where we see some vertical asymptotes. So instead of being at 0, we have one at -2. Instead of being at 0, it shifted to +2. Instead of being at 0, it shifted over to +4 would be our vertical asymptote. And then notice on this last one, there actually is no vertical asymptote. So what we're seeing on each of these is, again, the shift in where we would see these asymptotes occurring. So this is down at number 10, where we see the shifts of vertical asymptotes. So for the first one, f of x had one at x equals 0, g of x was at x equals -2, h of x was x equals +2, p of x equals 4, and then we notice that z of x had none. And this is going back to the idea of these denominators. And if you set each of your denominators equal to 0, that's going to give you where these vertical asymptotes are occurring. Notice officially why z of x didn't have one. If you tried to set x squared plus 1 equal to 0, your vertical asymptotes would be imaginary. So that's why there were none for z of x. Now, if we look then at number 11, we have our function, and then they're saying f of x minus 3. Now, if we predict, right, you might remember your horizontal shifting rules on this, but if we check out on here, here's our parent function, shifting it f of x minus 3 is actually shifting it to the right 3 units, which is going to shift our vertical asymptote from x equals 0 to x equals 3, since we moved everything to the right 3 units on that. And we're going to notice that pattern kind of continuing as we go on and look at some others with our asymptotes. Because for instance, if we look here with any of these ones in number 12, each time what's happening is if we have 2x minus 1, for instance, that is shifting our graph to the right 1/2. Or 2x minus 6 shifted it even more to the right there. Even though we have a coefficient, we're still moving over by setting that denominator equal to 0. So even though this time each of these graphs have a horizontal compression by 2, influenced by this 2 piece in front of here, the vertical asymptote is a fraction that's basically comprised when we set bx minus c equal to 0. So essentially each time our vertical asymptote is moving over there. So even though, right here we move to the right 1/2. Here we move to the right 3, because when we solve that little equation, that'll show us that little solution to where it moved. So again, if we check back to this graph and actually compare 2x plus 5, what we see is this is actually shifting our graph to the left 2.5, and then we are vertically compressing those still because of this coefficient on our x there. All right, now our last part then, if we look down at our piece here for then number 14, is asking us to add these together. So if we take our parent function, 1 over x, and we add it to 1/2, we notice a shift up If we add, aka subtract, 1 over x plus negative 3, it shifted it down 3. And then our parent function, adding 5, shifted it up. So what we see on these is these are going to be our vertical translations, up or down, by that factor d. And that overall leads us to a lot of information about these parameters. And kind of going back to what we talked about way back in Unit 6, parameter A would be our vertical stretch or shrink. Parameter B then is the horizontal compression each time if it's bigger than our value. So like for instance, since it's bigger than a value of 1, or a stretch if it was less. C over B we talked about will be the vertical asymptote slash basically that horizontal shift. And then D is our vertical shift up or down. So these are kind of important features, because then if we allow this to kind of tell us how we are going to overall be moving our different parameters. So for instance, on number 16, if we have 1 over x, and we notice that we are shifting it to the right 1.5 units, up 0.5 unit, vertically stretch it by 2, and horizontally stretch it by 2, a couple things that we would have to make note of. Okay, so for instance, we would have that vertical stretch up top, that's our parameter A, and then we would be translating it 1.5 units to the right, so we know that that is normally our x, to the right would be 1.5. And then a horizontal stretch by a factor of 2. It's actually, because it's in the denominator with that x, it's a 2 there. And then our shift up would be the 1/2. Now notice on this, something you're going to see with this compression is you might also see this distributed through, so that you would have 2x minus 3 and then up that 1/2. All right, so lots going on here, but in particular today again with the transformations and talking about some different features, we will definitely be working more with these movements of the parent function in class. Thanks everyone for watching.